So what I'm going to talk about is a few things, but basically what I want to share with you is one thing that I really love about math, which is the idea that you can have one mathematical idea or structure that's underneath lots of different applications or situations in the real world. And so I'm going to give one example of that, which involves clocks, chords, and roots of unity. So let's start with what I'm sure you're familiar with most of all, is the clock. I love this as an example of mathematics because it's so familiar to everybody. Everybody knows what a clock is. But it also kind of turns on its head what you think of as one of the most basic things about math, which is addition, right? So we all know how to do addition. That's the first thing, your first exposure to math, except I guess like counting. But even that's different here. So if in normal numbers, you would take 10 plus 10 and get 20. But if you're counting on a clock and it's 10 o'clock and you have to do something in 10 hours, we don't say 20 normally. At 12, we go back to 1. And so then you add 8 more and you end up at 8 o'clock. So now I have a statement, 10 plus 10 equals 8, which normally, if you just saw it out of context, you would say that's completely wrong. That's not how addition works. And yet there's this situation that we all see in everyday life all the time where this makes absolute sense. And so what we've done is changed the underlying mathematical system from the natural numbers, where you add up to infinity, to what's called the integers modulo 12, where you get to 11, and then you add one more and you're back to 0, and you start over again. And this idea comes up over and over again, not only in math, but other sciences as well. So I'm sure many of the scientists who are here have seen this before. But I wanted to share one point where it came up recently for me while I was working on my thesis. And that was regarding something called roots of unity. So a root of unity is a number that you multiply it by itself a certain number of times and you get 1. So if you're talking about square roots of unity, you want numbers that you square them and get 1. So you would have 1 itself, 1 times 1 is 1. And you could also have -1, because -1 times -1 is +1 again. If you're talking about fourth roots of unity, you want something you multiply by itself 4 times to get 1. So +1 and -1 still work. If you want more, you have to start using complex numbers. So maybe you've heard of the complex number I. I squared is -1. So if you square it again, you get +1. So I to the 4th is 1. It's a fourth root of unity. And since we just talked about the number 12 on the clock, let's look at the 12th roots of unity. Here they are. So all the numbers where if you take them to the 12th power, you would get 1. So of course there's 1 and -1. Those are the real ones. For all the other ones, you need to use some complex numbers. So we've got that weird little number I in there. And what's really one thing that's interesting about this is that if you take certain ones of these numbers, so if you look at the second one I've written, square root of 3/2 plus 1/2 I, if I call that W, and then I write all the other numbers in terms of that, I can actually write the one after it is W squared. It's that number times itself. And then I can actually be written as that special W times itself 3 times, so W cubed, and so on, all the way up till you have W to the 11th, and then if you do W to the 12th, because it's a 12th root of unity, that gives you 1, again, which is the same as W to the 0, so 0 exponent gives you 1. So what we have here is what looked like a whole mess of kind of random complex numbers, although clearly there's some pattern with the square roots and stuff. But when we write them like this in terms of one of them, and we can even put them in a circle here, we can see that once again, we've got the same pattern that we have on the clock. But what we're doing now here is instead of adding 1 each time, we're multiplying by a different number each time. So we're multiplying by W, and the exponents are going up 1 time. And you can go all the way around the circle, and then if you multiply by W again, you'll start over. So we see the same pattern here in kind of a more advanced mathematical topic, just like you see every day on the clock. And I'd like to do one more example of this, which is music. So you may know that there's 12 notes, the way we normally divide an octave. It's called an octave because there's 8 notes in a scale, do, re, mi, fa, sol, la, ti, do. But there's actually 12 notes if you do sort of chromatically every note. Then there's 12 of them. And you have the same pattern here, where if you're starting at C and you do all 12 notes and you end at B, and then you want to do one more note, it will be an octave higher. So it's a bit different, but it's the same note. It has the same sound to it. So we have the same repetitive structure here. And if you study mathematical music theory, your starting point is to say, well, we're going to look at this as the mathematical object integers modulo 12, and we're going to use what we know about those and apply it to music to help us study that. And so I would like to use what I know about the integers and music to share a song with you. And bonus points for you if you know why I've written the chords in this way, in this order. But what we're going to do is it's going to follow along with showing you what chord I'm on so that you can see me go all the way around the circle and get all 12 chords in. So we're going to start on A. I see the world a deeper way when I look at it through you. Outer appearance drift away. Would you show me what's true? I wish I had time, clock is ticking by. Give me one more try now. All right, C sharp, we're a third of the way through. The world a brighter way when I'm listening through you. Sorry. When the pattern shines through, my ideas are free, seeking unity. Be the root for me now. I face the world a smarter way when I'm facing it with you. You lead me through the disarray. Would you take me someplace new? I wish I could sing and these chords would ring with the joy you bring. But now we're back to the start. Let me say from the heart, I hope mathematics we never shall part. Second verse a little messed up there, but hopefully you got the idea. We made it all the way around the circle. Thanks.